Namaste everyone. In this video we'll be solving this particular problem which is given on conduction and convection. So we have a wall which is 0.5 mm thickness and it's having a thermal conductivity of 6 watts per meter Kelvin, and this wall is to be insulated with a material of thickness 0.1 meters which is having an average thermal conductivity of 0.3 watt per meter Kelvin. So let me start by drawing this wall. This wall is the inner wall and we have another wall coming over top of it. Fine. So this surface, there is no limit or height given for the surface, so we'll just assume that we're extending on both the sides. So let's take down the given data for now. So thickness of the walls has been given to us. Thermal conductivity for first and second element has also been given. Thermal conductivity of first wall is 6 watts per meter Kelvin. Second one is 0.3 watts per meter Kelvin. Now we need to draw the diagram for this in terms of nodes and elements. Fine. So there are actually 3 nodes here. The node numbers as 1, 2 and 3. And there are 2 elements here. Fine. 2 elements. So this is the first element, this is the second element. So this is just a one-dimensional problem because there is no heat or temperature variation going in up or down direction or towards or away from us. So the temperature variation and heat flow both are occurring in a single direction. So this is considered as one-dimensional problem, and this is the nodal diagram for the same. Let's just see what are the other values given to us. We have been given the inner temperature. So the value of temperature here at T1, that's 1200 degrees Celsius, and the ambient temperature, which is written as T infinity, atmospheric temperature, which doesn't change no matter how much heat is removed or added to it, that's written as T infinity, that is 30 degrees Celsius. And the heat transfer coefficient at the outer surface has been given as 40 watts per meter square Kelvin. So starting with this data, we should be able to find the temperatures located at all the nodes. So first let us start with the relation. Fine. So we need to find a relation between thermal forces or the heat flow equation, and that heat flow equation will be equal to the global stiffness matrix, global thermal stiffness matrix, multiplied by the temperature matrix. So this is the equation we'll be using in order to find all the temperatures. We should be able to expand all these and write them down. So let's first expand the thermal forces. So that's will be very simple: Q1, Q2 and Q3, and these Q1, Q2 and Q3 are the heats which are flowing in or out of the total system that we are considering. And Q1 is the amount of heat which is coming in at node 1, that's unknown, so let's keep it as Q1. Q2, there is no heat either coming in or going out, so that's just 0. About Q3, we know that there is convective heat transfer going out at this point, and that's going to be H into A into T infinity. So while using the temperatures, we should actually be using the Kelvin values of it. So we need to add 273 degrees to this, which gives us 293 in Kelvin. Similarly, the inner temperature gives us 1473 in Kelvin. So these are the values we need to substitute. So using these values, A, of course, the area will always take it as unity because it's a one-dimensional element and area doesn't matter. So substituting these values, we will get the heat that is flowing at this point. So when you do the calculation for the heat flowing out, the convective heat, we get it as 11720. Next, let us find the temperature matrix. That's T1, T2 and T3. So T1, T2 and T3 are temperatures at the 3 nodes. T1 temperature is known to us, that is 1473, it's given. T2 and T3 however are unknown, so let's keep it as it is. Coming to K, this is the global thermal stiffness matrix, and its value is equal to the local thermal stiffness matrix for element 1 and local stiffness thermal matrix for element 2. So let's find the local thermal stiffness matrices at both the points first, and then we will combine them to form global stiffness matrix. Since in the first element it's only undergoing conduction and there is no convection, so this is the global stiffness matrix, the local stiffness matrix for it. Calculating the value, we get 12, which needs to be multiplied on the inside. So this is the local thermal stiffness matrix for element 1. The second element is not only undergoing conduction but also convection, and the convection matrix is H times A, and convection we can see is only happening at the rightmost surface, so all other values are going to be 0 except for this last term. So K2A2 by L2 will give us just value of 3, which if you multiply on the inside we get 3 minus 3 minus 3 and 3, and if you take this value over here, that's 40 times the area, which is just unity, so that's just 40. So multiplying the 40 inside we get zeros all the way, and here we get 40. Adding these two matrices we get the final values as 3 minus 3 minus 3 and 43. So this is the local thermal stiffness matrix for the element 2. Now we need to combine both of these, and while combining we should be careful about the nodes. So these are the nodal values for the first element, whereas the nodal values for the second element are these. So when we are writing the global stiffness matrix, we need to be careful. We need to write we need to consider all the 3 nodes for the global stiffness matrix. So this is how we need to write them. So 1 1 will give us this value. Let's write them down over here. For 2 1 we just have one value, that's minus 12. Same way for 1 2 as well, we just have one value. When it comes to 2 2 we have 2 values relevant with this, so both these values need to be added at this point. So 12 plus 3 will get is as 15, and then about the other values we just need to write them down as it is. Now for whichever combination of nodes we don't have any value in both these matrices, for those we just need to enter values as zeros. So this is our global stiffness matrix of K. So once we have found all these matrices, we just need to put them back in this format and we need to just solve them. So let's take the first matrix over here, that's the thermal matrix. So this is equal to the global stiffness matrix, global thermal stiffness matrix. This needs to come over here, and then this needs to be multiplied with the temperature matrix, which comes over here. This is the matrix. Now we can see that there are a total of 3 unknowns in here, and these 3 unknowns we can easily find by one by one by solving these matrices. So first we just need to ignore this because the Q value which is here is unknown. So that gives us the value of T2 as 1250 and T3 as 359.79. So both these values are in Kelvin, which we can convert back into degrees Celsius. So that gives us 977 degrees Celsius and 86.79 degrees Celsius. So these are the 2 temperatures that we have just found, and by substituting these 2 temperatures into the first equation we can find the value of Q1 if needed. So that's it for this video. We'll see you in another video with another problem like this. If you get any doubts about this, you can let me know in the comments and I'll try to clear it. Thank you.